Okay, let's resume. So for this part, we're gonna try to implement the scheduler, which is called multi-level feedback queue to the XV6. I think this part is much more challenging than the first project B, part 1B, because as you can recall, for previous XV6 project, it's just like a warm up, right? So you don't need to do anything particular. Just basically look at what get PID does and then basically mimic what it does, and that's it. But for this project, yeah, you have to not only look at a lot of code, but also you have to try to really do some debugs thing if you get stuck on some particular code. So but I think the high level, conceptual level for this project is very straightforward, right? So and also the easy part of this project is that most of the code you are gonna write is very centralized. It's just localized at the file called kernel proc.c. So this is basically what you will look at very specifically. And you will also just look at scheduler, the method here. So this is what the real scheduler is doing here. So all you need to do is just first understand what's the original version of the scheduler does, and then try to add something here. So basically this is what you should look at particularly. So anyone has an idea what's the original version? I mean, what's the scheduler for the original version of XC6? What's the policy? Exactly. That's so. Originally, it's just round robin, and here I can show you. We can write a simple user program in XC6 and try to print out something and have a feeling that it is real round robin. Okay, so in this part, I only added this output. So by the way, in kernel, if you want to print something, you should use cprintf instead of printf. Okay, but the cprintf, the grammar or the syntax is exactly the same with the Linux C printf. All you need to do is add a C before it. But in the user program of x86, although it's called printf, you should add the file descriptor as the first argument, and then followed by the string and the variables. You have add the file descriptor as the first argument. So if you want to print it to standard out, then the file descriptor is 1. If you want to print something to the file, then you open the file and print out to the file descriptor. Okay, that's some tips for the output, which is I think the most useful tool for debugging. Right, some people were probably not very comfortable with GDB. Then the best way to debug is to either cprintf in kernel or printf with the extra file descriptor argument as the first argument at the user program. Okay, so here I only print the PID of the process that gets scheduled. Right, so you can see at this line we just assign the running state to this process, and then we print this process to see which process it's running. Okay, and how to write a user program. Sorry. So I have a hello.c here. So when you initiate the XV6, you finally will get the shell, right? The shell from the XV6, and shell itself again, it's a process. But here I want to just see, because it's round robin, right? So I want to create 3 more processes so that I can see a real, very obvious pattern for the round robin. So here in the main function of the user process, I just create 3 processes. And how to create processes? Again, use fork. Right? So because I want to create 3 processes, so I can have a for loop here. So and then I'll just skip the PID because I don't care too much about the PID. So fork, if this is 0, then it's a child, right? So here we'll do something. Because the scheduler, let's just try to have a very some workload in the process that takes some time, right? Because if you just like do something very simple, then you may not have time to see the pattern, and then this program just finishes. So let's just try to have like a while loop inside the child. Let's just have a counter, right? Like I think 1 million is not enough because I tried before. 1 million is like very short time because so I probably add 2 zeros at 0.1 billion and count plus plus. So this is a very sensible. It's a sensible workload, and I issued basically I forked 3 processes. But after this workload finishes, you have to exit. Otherwise, something weird will happen. If you do the worksheet, you understand why should I exit. If you don't, then you should remember to exit because something wrong. Until you finish the worksheet. Okay, I will not talk too much about worksheet, but okay, I'll exit here, and then okay, and at here I should wait for the 3 process to finish. Right. So wait, that's it. And finally, for the main, I also need to exit. Otherwise, I'll get some weird errors from x86. Okay, and don't forget to add this hello to make file.mk. I have added, but in case you forgot, you should add it here so that the compiler knows the existence of this program. Okay, let's just make QEMU. So, you can see why are we having this? Because we see printf something in the scheduler, right? So what is PID equals 1? That's the very first process, right? Which is the very first process is different from all the rest of the process, right? The very process is not created by fork because no one is forking this process before 1 because it's the very first. So this process is very special. So it's created at boot time of x86. I'll just skip the details of this. But for the second process, for the second process, it's actually just the shell for x86. So the shell process is created by the very first initial process. Okay, and then now let's try to run the hello program, the user program just now we have. Let's see. So this time stick is actually from the shell, right? PID2. And it actually tries to fork our hello program, right? And then what's PID for fork? It's actually just the hello program, aka the main program, right? The main function. And the main function forks 3 processes, which is 567. And now this 567 has a pattern of round robin, right? Exactly round robin. And after that, after they finishes, and here I think is the parent of these three guys, which is the main function, right? The main, which is hello, and it waits, clean up some states for these three processes. I'm not sure why 60, but yeah, some. And then finally it gets back to 2, which is the shell. And shell will prompt wait for the second process, next command, right? So it's basically just a very simple round robin. And yeah, this is a very easy demonstration.
How did you compile your hello.c? I can't get into the dial.
You should add hello into user/makefile.mk so that the compiler knows the existence of hello, and then you just type make, just compiles both kernel and user programs. And then how you just try to make QEMU -nox, then you will just start booting the x86. Okay. Okay, now let's take a closer look at the scheduler. Okay. So did Gerard in class go through the scheduler function? He did. Right? He showed you guys some part, right? Okay. So scheduler. Okay, so it's here. So basically, this is a forever loop, right? This is just a forever loop, and here in each, so for each iteration of this forever loop, it just represents one timer tick, a time tick. Okay, so in the specs, let's see. So for sorry. So you guys, I think you guys have some understand the terminologies, right? So time slice is essentially some multiples of timer ticks, right? So for like priority 3, the time slice is like 8 timer ticks, okay? And for each timer tick, it just corresponds to one iteration of that forever loop. Okay? So basically for this, each iteration is just one timer tick. And if a certain process gets scheduled here, it just consumes one timer tick of that priority. Okay. Now, at this line, what does this line do? This for loop do? Essentially, we just loop through the p table. So, what is p table? What's the data structure for? What does p table store? Right, exactly. So basically, the p table just stores a list of the process. So each element of p table is just a PCB, and for specific process. And when you iterate through this process, the p table, you look for a specific runnable process, and then you start to schedule it. That's basically what it does here. Okay? And once it selects this guy, you will set the state to running from runnable, and then you do the magic thing here. So I think you should be familiar with this guy, which is our old friend switch, the context switch, right? Now you can see, originally we are at the context of the scheduler, right? And now we switch from the scheduler to the chosen process. Okay, because we are choosing this process to run, and then we just switch from the scheduler to the current process, to the process. Then after this switch, where are we going? We just go back to whichever process is, right? And then that specific process will have like the next instruction, like the PC of that process, and then we'll continue running that process. Okay, this is what context switch is for this scheduler. And then after some period of time, like timer ticks or system call or like errors, we will go back to the trap handler, and the trap handler just call yield, right? And yield will just switch back from that specific process to the scheduler, and then we just come back here. Okay, and then we'll finish one iteration, which is one timer tick. And then we look through the p-table again to see another runnable process. That's basically the cycle of this schedule, what this scheduler does. Does that make sense? So let's take a look at so if you have like trap bus. So this is basically just a trap handler, right? So when you like system calls or like a timer interrupt, you have different cases. And here, for example, is a timer interrupt. So this is just a timer interrupt happens. So if timer interrupt happens, then we'll force the process to give up the CPU. How do we do that? We call yield, right? And what does yield do? Yield just set the process, the state of the process back to runnable, right? And then we call scad. What does scad do? So with some if statements, and finally we see another switch. Now let's take a careful look. For this time, switch is from the process back to the scheduler. So essentially, you can regard scad as an opposite way of scheduler. So essentially, in scheduler, we switch from the scheduler to a specific process we are going to run. But for scad, we switch from the process back to the scheduler. So basically, scad, you can actually it's better to call it deschedule, right? So scheduler versus deschedule is just the opposite way. So that's basically what scad do. So again, when timer interrupt happens, we get into the trap handler, right? And trap handler see the number, okay, oh, it's a timer interrupt, and then we call yield. And yield calls scad, and scad just switch using context switch, we switch back from the current process to the scheduler. Basically, the scheduler just that process just give up the CPU, give back to the scheduler, and scheduler will look through the p-table again to see another runnable process and schedule. That's basically what whole cycle is. Okay. So I'd like to talk more about the p-table here. So if you search p-table, I think at the very beginning, it's actually just a struct. It's got a field of lock. So why does p-table has a lock? So lock probably, yeah, in chapter 3, we'll talk more about the lock things. But right now, you can think lock as like a protection against the race condition or the concurrencies of two separate processes. So we if you provide the lock, then there will not be interference from one process to the other. So just protect the process such that they are not intervene with each other. And next, which is the most important one, is the actual list or an array, right, that stores the proc, which is the struct defined at proc.h. So this is the struct defined in proc.h. It's actually just a PCB, okay, with multiple fields. So the hint for this process, for this project, is that you should try to add some field in the PCB so that you can keep track of how many time ticks this specific process has used and which level this process is currently at. Right? This completely makes sense. Right? There's no need for you to have a separate data structure to store the information of that process. You can just put everything you need into the PCB. This is a very convenient data structure. Right? You don't need to create a new one. Just add more here. But try not to modify the previous one. Right? The original one, try not modify it. Just add more. That's fine. So yeah, that's a clue. That's a hint. You can just add the timer ticks, the process used, and also the priority level the process currently is at, so that you can keep track of for the multi-level feedback here. Okay. Oh, by the way, I think some students have probably thought too complicated because it's called multi-level feedback queue, right? It's a queue. So some people think, well, should we have a fancy data structure, like queue structure, to maintain these process states? You can do that, or you can have a so-called fancy. You can like even create a linked list to maintain so that there was no gap between. That's okay, but again, it's kind of overhead to this project, or overhead to your own like time, because you have to spend a lot of time doing that. I would suggest that you guys try not to use this fancy data structure, just based on this simple, naive way, right? Just as what p-table does. P-table is just a array, right? It's not a linked list. So just maintain this array and try to add fields to keep track of the information. That's totally fine. Okay. Okay, this is simple for p-table. And I want to also try to help you guys look over the p-table. So when does the process gets added to the p-table? Because initially the p-table must be empty, right? And as long as there's one process created, that process will be added to p-table. And when does that happen? It's actually at alloc proc. So alloc proc, this function is also very important. You should try to look at it. This method is just creating some necessary information and then added to the p-table. So you can see, you scan through the p-table, right? And then you find a position that's not used, and then you go to found. I think go-to is not a very good practice in any of programming language, but since this x86 code is like years old, so there are a lot of go-to here. So that's fine. After all, it's a very like low-level kernel stuff. So try not to use go-to in your like object-oriented programming, but for this, probably it's fine. Okay, now if you find a position that's available, then you can try to construct the new entry for that p-table and store the information of the newly created process. Okay. Probably not care too much about this. But you will go back to this chunk when you do project 3. But right now, I think that's totally fine. Yeah, don't look too much about it. You just know what alloc does. Allocproc basically just look through the p table and find a empty position and put the information, all the necessary information of that newly created process into here. Okay, and who calls allocproc? User init is just the initial process. We don't care about it. Okay, so allocproc happens at fork. Okay, that makes sense, right? Because fork creates a new process, and every time you create a new process, you should put that process information to the p table such that the p table knows it. Right? Otherwise, the scheduler will not know the existence of this new process. Right? That makes sense. Okay, now let's spend some time to take a look at what fork does internally. So this is, we create a new process and put it into the p table. And here, again, it's probably you should look at it for project 3, not this project. But for curiosity, this part is essentially creating the address space for that newly created process. This is for memory management. But right now, you probably don't care about too much about it. And here you can see, okay, size, this field is essentially maintaining the memory size of the process, probably also not care too much about it right now. And here is a very important one, right? So proc is actually the parent, and the NT, which stands for new proc, which is the newly created process returned from alloc proc. So basically, we say the parent of the newly created process, it's proc. Right? This makes sense. And here we just copy everything from the parent's trap frame to the newly created trap frame. So fork, again, just basically copy everything from the parent, including trap frame. And here is, okay, this is for like the file system thing. It's actually just copying the file descriptors from the parents. And we can see here, just now the example, right? You create some file descriptors in the parent, and then when you fork, you have like, every child has its own copy of the file descriptor. That's what it does here. And finally, we assign the PID, and we set the new process to be runnable. And this is just for copying the name of the process, the string. And then finally, we will return the PID. That's basically what fork does. Okay. So, any questions so far? So far, so good? Okay. Now let's take a look at another challenging part for this process is it's not the scheduler itself, but it's actually the second part, the creating new system calls. But I think you've already created the simplest system call at P1B, right? But that one is, if you recall it carefully, that system call actually does not take any argument. You just get PID and void, right? But now, for this system call, actually we have input argument for this system call. Probably you may take it for granted. You think, well, the void argument or n argument isn't almost the same. Actually, this is not a trivial issue. So I think I should spend some time to talk about how are we going to create the system calls. So let's just start from the system call for kill. Again, let's have our user program here. Okay, so in XV6 we have a system call called kill, and it just kills a specific PID process with the specified PID. For this demo, let's just try to have an arbitrary number because I want to show you how this argument gets passed from the user mode to the kernel mode. Okay. So again, if a function is not a system call, like a regular function at the user program, that argument you pass it. That's very simple, right? Just put it onto the stack, and then do whatever the function does, and then after the function returns this, the stack just you can reuse the stack and something like that. That's very simple. However, for system call, you have to trap from the user space to the kernel space, right? And then the argument you passed here is actually stored at user space. The tricky part is how are you gonna pass this argument from user space to the kernel space? This is a non-trivial problem. Okay. Now let's use GDB to go through kill and then have a feeling of it. Okay. So again, as a revision, let's try to use GDB, and then I have GDB here, and then here just have GDB. Let's add symbol file. Does anyone remember which line is kill? sorry, I need to. Okay, line 18. Okay. Let's do that again. GDB. Okay, add symbol file. Okay. Now let's set a breakpoint at hello.c 18. Okay, line 18. Let's do. I'm not sure why the shell constantly fails. Probably because I'm also trying to do screen record, but never mind. Okay, let's call the user program we wrote just now at the XV6 shell. Okay, at the very end, we have kill, right? So this previously it's just for the count, right? The 0.1 billion loop and then finished. And now we hit the kill. And now you can see GDB, right? At 18, we hit kill. Okay. That looks very simple, right? And let's step into it. Okay, before that, let's take a look at the stack pointer of current process, what the stack pointer is. So for this, to get information for the stack pointer, we can use info register and the ESP. Or we can just, for short, you can say IR ESP. So right now, the stack pointer points to this address, okay? Actually, you can also just type IR to see the full list of the registers. But right now, we are only interested in the ESP, which is at this address. Just take a note, because we'll probably get back to this value. So just write down on the paper or whatever. Okay, this value, okay? So now we are about to step into kill system call. Now let's step next. Okay, after we push the 8, the value into the stack, let's take a look at what USP is now. Okay, so it's at 1FB0. So what value is stored in this address? It should be 8, right? Because we push 8 into the stack. So if you don't believe that, you can try to print and dereference this address, right? You can see 8, right? So the number 8, which is the argument of kill, gets pushed into the user stack, which is at here, okay? And now we call kill, not stack. Okay, now we enter the syscall, which is the assembly code of usys.s. You modified it in P1B, right? So you add syscall, get PPID, something, right? So this is the assembly code. And then you step. Okay, now you push the number 64, which is the number of system call, right, into the vectors. And then you notify the system that, okay, it's 64, which means this is a trap from system call, okay? And now you jump to the trap handler. And in this trap handler, you store a bunch of the registers to the kernel stack. This is not too much about it. Okay, now finally we'll call the trap, right? We'll enter trap.c. And we'll see if this trap number is system call, which is 64. Again, I think I remember last time I also stepped into this, but turns out you can go to the next step. Next step. It's actually not into this if statement. The reason is that because another trap is timer interrupt, and we are debugging here. So debugging is take a very long time. So timer interrupt can happen anytime, basically. So we can easily get trapped into the timer interrupt instead of the system call. So debugging into this part will sometimes lead you to some unexpected traps, because timer interrupt basically happens every timer tick, right? And we are doing this and takes multiple times of timer interrupt, so it's very easy for us to get trapped into the timer interrupt instead of the syscall we want to get. So the best way to do that is we just create another breakpoint because it's system call of kill, right? We just go into syskill and let's run continue. Okay, now we are into the syskill. Okay, let's take a look at the code. So this is what syskill does. It's at kernel/sysproc.c. Okay, so let's take a look at it. It's a define a PID. Okay, I'm not sure if you've noticed, syscall itself does not take any argument. It's a void. But our real kill system call essentially needs an input argument, which is 8 for this case, right? But actually, syskill does not take any argument. Then the tricky thing is, how are we gonna pass the user from the argument that is defined in user space into the kernel space? That's a tricky thing, because now we are at kernel space, right? From trap. Exactly. So I can have a plot here with the diagram. So again, this is like the address space of the process A. So I assume at high, this is like high address. low address. So the stack will basically grow from high to low. Right? And so at high addresses, essentially this is the kernel stack. Right? And at low, somewhere we have like user stack. Right? Each process has its own user stack and its kernel stack. Okay. So our user program, like hello, .c, the code and data is somewhere here, right? It's stored in the user stack. And when we call kill 8 in hello.c, we essentially put this 8, this argument, to the stack, to the user stack, right? All right, here. So essentially this is going to be ESP, and we push 8 into here. So that's why I asked you to remember the value of ESP after we pushed. I think it's so it's here. So after we push 8 to the stack, then we see the ESP. It's got the value of the address is at 1F here. Okay? And in this address, which is here, we store the value of 8. AKA, we can dereference this address, and we got 8, right? So this is what we do here, right? We get the content or the value of this address, we got 8. Okay. Now we are trapped into the OS, the kernel stack, right? And now we are at the code of here, right? The syskill, somewhere here. How are we gonna get the value of 8 from user stack? We can actually look at the ESP right now. You see, it's a very huge number. It's like 6 digits, but here it's got only 4 digits, which means it's at the kernel stack. Oh, this value is not very important. Okay, so this is ESP. We're not at here somewhere. How are we gonna extract the value stored on user stack? Because we need it, right? Because we have to kill the specific PID. We have to know where is this number 8 stored. Anyone has an idea? So when we call a system call, we just trap from the user stack to kernel stack, right? And at this step, what does hardware do? Right, the hardware stores a list of registers, right? At where? It stores the registers just at kernel stack, right? The registers of whom? The registers of user stack, right? So basically, the hardware, upon trap, hardware stores the registers of the user stack to the kernel stack. So actually, we do have a way to refer to the wherever these registers get stored somewhere here and refer so that we can have we'll extract the number for this register, right? So in particular for this X6, hardware stores the registers in the data structure called trap frame, right? So each process has got a field of TF trap frame. I think I need to open another thing. So it's a demo. So demo proc.h. So you can see the PCB of proc here. It's got a field called trap frame, right? So essentially, for XV6 particularly, the hardware just stores the registers from the user space to the kernel stack, which is at the trap frame. So you can always refer to this data structure to get the registers from the user space. Okay, so you can also look at the data structure of trap frame. Probably TF. Probably not here. I think. That's a lot. Oh, I see. I think it's not at kernel. It's at sorry. I think it's in the include, right? Traps, yeah. No, not here. Sorry. I think it's at x86. No. Oh yeah, here. Sorry. Yeah. So the trap frame's data structure is stored in x86.h. So what does trap frame store? It just stores a bunch of registers from the user stack, including the ESP, EBP. Yeah, ESP is here from user to kernel. So the trap frame. So basically, we are right now at here, right? So if you refer the ESP stored in trap frame, you will essentially get the ESP of this value, which is at the user stack you stored by the hardware. Does that make sense? So in short, in order to obtain the arguments in user stack at kernel, you can refer to the register stored at trap frame, and then you can get. So essentially, this ESP is exactly the same as this guy, and then you can refer this to get the value from user stack. Okay. Now let's take a look if it's the case. So now we are at 33, which is this line, right? So it's a function probably you are not very familiar. Let's go into argint, okay? Step into argint. Now we are in argint, right? And argint returns fetch int. Let's go to fetch int. Step into fetch int. So let's see this line 48. So let's see the fetch int. There are like 3 arguments. Do you see something familiar? Right? This is just the ESP stored in the trap frame or the kernel stack of that process. The reason is that this ESP is essentially the same with the ESP last seen in the user stack because we store it into the trap frame. Now, what is +4? +4 is 4 bytes, right? So essentially, Oh, okay. So this address stores 8, and I think this address, like B0 minus 4 is AC. It stores the return address of so basically, again, when we call a function, right, we not only push the argument into stack, but also we should push the return address of kill into stack, right? So yeah, so we have, so I think the ESP here stores this value. Let's take a look. Yeah. So you can see the fetch int takes in the 3 arguments, right? And when we step into fetch int, we got essentially these 3 values. The middle one is the address, which is 8112. This is decimal. You can try to print into hex, which is C. So it's exactly 1FB0. So 1FB0 is this guy. This is the address. And this is from the proc TF ESP plus 4. For n, I think it's 0 because argint is the first argument is 0. And yeah, argint takes n equals 0. So 0 is just 0. And ESP plus 4 is address, which is 1FB0. So ESP is essentially this one. This is just ESP. This plus 4 is the address. Does that make sense? We can plot this in detail. So in user stack, the first argument the first thing you should push to stack is 8, right? It's the address of 1F0. And this stores 8, right? And then you should push the return address of kill into stack. This is from the function call convention of x86. So this is 1F. Okay, let's try to got a reverse way. So this guy minus 4 is C. It's correct. So this is higher value. This is lower value. This is the return address. Oh, yeah. So because stack goes this way, right? From high address to low address, every time you push this way instead of this way. So every time you push in this direction. This is for push. And you first push 8, and then you push the return address. So after you push the return address, your ESP is here. And you get trapped into this kernel, so you store the ESP of this value to this stack, which is stored in the chapter. So that's why you need to add 4 bytes to get where this argument gets there. Does that make sense?
I understand the step pointer line would add 4 bytes, but I'm kind of confused about why it seems excessively complicated to me to call argint and then call fetchint.
I think all this stuff is just trying to get this number 8. That's it.
Isn't
And
it-
how are we gonna get 8? First, we need to get the ESP. And how are we gonna get ESP? Use this. So it's stored in the kernel stack. But ESP is in the user stack. How are we connect it? The way to connect it is because hardware just stores the registers for the user stack to the kernel stack. And this is as kernel stack. So we can refer this from kernel stack to get the user stack.
What are the functions argent and fetch? Couldn't you have just written in Cisco to get the value from RTF?
Did you mean here we can just directly, instead of calling like argument, we can directly call return kill and
Yeah. Didn't you just put kill and then put the arguments and fetchant into there? I guess I don't understand why you're doing argument and then fetchant. Maybe I'm just missing something.
okay, so initially, this you declare PID, you do not have the value of PID. It's like
And that's where you're going to the cat frame to get it because it's
right.
on the stack. Okay.
Right. And then, and actually, in Argent, we can look at the code. So where is Argent? Syscall, kernel syscall. Okay. So when you look at kernel syscall, it's very simple, just one line. Sure, you can just don't call argin, you can directly call fetching. That's totally fine. But it's just like the reason for the existence of argin is that we have other functions called arg pointer to fetch the pointer for the strings, and also the arg string to fetch the strings stored on the user stack. So like for completion, we just have an argument here. But internally, it's, yeah, sure, definitely, it's just calling fetching. Does that make sense?
Okay. Maybe I'm still confused.
Why we use fetching today? Okay, let's see what fetching does. So fetching here, okay, this is the final step. We want to get the number stored in the address to the PID, which is for this case, right? So IP is actually you put PID here, right? So IP is corresponding to the address of PID. So essentially you fill in the address of PID to be the address of ADDR, which is this value, this address. If you reference this address, we got 8, right? And you assign 8 to the address of PID. That's basically what this step does. And before that, it's just checking some sanity check. You have to make sure that the address you got, it's not out of the boundary of the user memory. So that's what fetching does. It's just, aside from this sanity check, we just do this simple thing. We just, because we have already got the address, right? And then we assign, we dereference this address to fetch this int, and then finally assign it to the PID. That's basically what it does. So that's yeah. I think this part is very tricky because you have to think of a way to connect between the kernel space and the user space. one way to do that is through the trap frame, because the hardware has already stored the registers of the user space to the kernel space, and you can, when you are at kernel, you can just look up into the trap frame and get that register like ESP, and then okay, I know that address. I will dereference that address to fetch that value, and then assign it to whatever you want. Basically, for this case, it's a PID. So another thing is that why do we have like 4 times n? But for this example, it's 0, right? 0 does nothing. But why do we have 4 times n here? That's another tricky thing here. Because in this example, here we only have one argument, right? So definitely we can have a system call where like we can have multiple arguments, like we can have 3, A, B, and C. So if we have like 3 arguments, again, we should first push them into user stack. So the order is, we will reverse the order. We'll first push C into stack. We do this way, okay? This is C, and then we push B, and then we push A, and finally we'll always push the return address, okay? And now ESP points to here, and now you are in the you are trapped into the OS, which means this register together with other registers which we don't care about right now, we only care about ESP, will get stored into the trap frame, right? Stored in the kernel, so that in the kernel we can refer them. We can refer to them. And now you are calling. You are having ESP plus 4 plus 4n. So ESP again, you are at the return address. So you plus 4, you get the first argument, which is corresponding to n equals 0. Right? If n is 1, then you plus 4 again, you get the second argument. If n is 2, then you get the third. So n is for basically where you have multiple arguments. You just get them one by one. Does that make sense? All right. I think that's basically it. So for this project, there are 2 parts. So I think this is kind of off topic, right? Because this has nothing to do with schedulers, but this is very important because yeah, in the first project we don't need to consider it at all, simply because we don't have argument in the system call. But if we do have arguments, then we have to look at this very carefully. How are we gonna receive arguments from user space to kernel space? That's very tricky. And it's worth the time because not only for this project, but also for the next like 3 projects, 3, 4, 5. I think basically every project for the XV6 in the future will involve, you have to write a new system calls. And maybe most of them will have like arguments. Right? Actually, void argument is very rare. Almost most of the time you need to pass arguments to the system call. So yeah, that's it. So any questions so far?